Hello, this is Lady Tehila from the Covenant of the Open Mind, Elder of the Open-Minded Path, and you're watching Metaphysics 101. Hail and welcome. The topic this time is quantum gravity. This is the second of two lectures that describe the dual nature of the universe, the fact that it exists in contradictory states that don't make sense. If you haven't seen the previous lecture, I strongly recommend that you go back to that first because it explains string theory. If you recall back from many lectures ago, I mentioned that we're going to reconcile the difference between a background-dependent and a background-independent universe. What do those terms mean? If you remember back to when we talked about general relativity, the description of gravity in the cosmos, in the astral realm, is background independent. Okay, what that means is that the universe itself, space and time itself, are influenced by the massive objects found within space and time. As we said then, the universe is not a stage on which processes act, okay? It is an ever-changing stage that is influenced by the nature of the actors. We didn't really talk about this much, but quantum physics, particle physics, the math of it depends upon the nature of the background to be fixed. It is processes unfolding on a fixed stage. And you can't really do quantum mechanics, you can't really do that physics if the background, if the stage is constantly changing. So they came up with a new theory. It's called quantum gravity, or specifically we're going to talk about loop quantum gravity, though we're not going to get too much into what it means for there to be loops. If you're really interested in it, I highly recommend this book, 3 Roads to Quantum Gravity by Lee Smolin. Excellent, excellent overview. Not a lot of math. It's very dense and hard to get through. I mean, I've read this book like 4 times. It took me many times reading the same things over and over again to understand it. And I'm going to reference it a lot as we go through this lecture, which is going to be very technically dense. And in the next one, we're going to get into the metaphysics of what a lot of this stuff means. This one's just going to give you the information that you need in order to understand the metaphysics. So let's start with a review on background independence. Okay, all things in the universe are really defined as a relationship between fields, between items that interact because of fields. So if we go back to reviewing what background independence means, it really means that all things are defined as relationships between fields, which can appear very different, but be identical because of the way they interact. So for instance, take a look at this picture here. These 4 circles look very different, and they appear in different parts of the image, but they're all technically the same in a background independent picture because of the intersection being the same. The ratio between the intersection between these circles is all identical to the size of the circle and the shape of the circle. Okay, so if you remember when we talked in the first lecture about universal truth, we said that the only real objective truth that you can define is a ratio between things, and that's the case here. All of these have different frames of reference, but the ratio is the same. And that's what makes them fundamentally the same in a background independent picture. Now, the next thing that you need to understand is that there's really no such thing as non-action, because a world in which nothing happens has no time, has no measure of change or distance, and this is what really defines the theory of background independence, right? The requirement for general relativity. So one cannot ask a question like, in the absolute sense, how fast is something changing? You can only say, how fast is something changing with respect to the way other things change. In general relativity, it's absolutely absurd to describe a universe that has nothing in it. It would be like saying a sentence that has nothing in it. Even a sentence with one word, for instance, stop. Okay, it's a valid sentence, but it doesn't make sense if there aren't other sentences or some other context to describe what it is that needs to be stopped. The only way in order for a sentence to make sense is for you to have more than one word that relate to each other and therefore provide meaning. Therefore, the universe is only defined by the order of the words, right? where the objects are in space in relation to each other, and what each of the objects is, what each of the words means, independent of the rest of the words. Together, the meaning of the words, the location of the words in the sentence, that describes the meaning of the sentence. A universe is like a sentence. It is defined by what it contains and the nature of the things it contains. Now, the next thing we have to talk about goes from the quantum side of things. So that's the general relativity side of things. Now let's talk about particle physics a little bit and recap, okay? So in particle physics, you have particles which exist in superposition states. That means that they are literally in multiple places at once, in both time and space. And until you ask them where they are, they're everywhere. So what you find from this is that the entire universe is, in a sense, in a superposition state, and it's only determined to be in a finite state, to have a single timeline and a single reality, because it's observed. That really bothers people in science. A person should not have to observe something in order for it to be physically considered real. And rectifying what this means is very challenging. It would mean that there's a picture of reality that has real but impossible alternate timeline. And what you find when you look at the math here, when you try to interpret what it means, is that there really are an infinite number of possible worlds, and there's no way to objectively know which one is more real. There's an infinite number of consistent worlds that have been classical up to this point, just like ours, that won't be anything like ours in 5 minutes' time. And so this is where the idea that, functionally, whether or not dinosaurs actually existed and whether or not fossils just existed in the past, came into existence from the present in the past, functionally those are the same. We don't have any right to deduce from the existence of fossils now that dinosaurs existed on this planet 100 million years ago. The fossils could have come into existence in the past. Functionally, those are the same. And that's why it's not violating the laws of physics to believe that the universe was created with a past. That doesn't violate any laws of physics. Another way to say it is that this world contains many different equally consistent histories, each of which can be brought into existence by asking different questions. And the way that this is resolved is that it turns out that you're not free to ask just any question. Only certain questions are valid. So rather than sitting here and asking which quantum depiction is right, you really just have to accept that all of the depictions, all of the different ways that you could interpret the way things exist are correct, are right, are acceptable. And the way it works is that if two observers are able to ask the same question, then they should get the same answer. If you ask different questions, you may get different answers, and those answers may not be comparable, and that's okay. So what we're really describing here is a universe that it's not many universes really, it's many observers inside of one universe. And there are many different mathematical descriptions of the universe, each corresponding to the different way that a different observer can observe the universe, considering that every observer is a part of the universe. Each description of the universe is in a sense incomplete because no one observer can observe the entire universe. They can only observe what they can see for themselves. So we're once again finding that the only objective truth here is the ratio, right? The only objective truth is the relation between two observers. So if two observers ask the same question, they have to get the same answer. And this really is a foundational truth that is uncovered as a logical consequence of both the math and the conceptual understanding of this math, and that is that the universe is observing itself. There's nothing outside of the universe observing it. The universe is observing itself. It is one universe with many observers. Now, the next thing that we need to understand in building towards a theory of quantum gravity is causation. What causes what? What is the effect and what is the cause? And this is summarized in a principle called light cones. It's not even really a principle. It's just kind of a descriptive model for what it means for something to cause another thing. And this is necessary because technically everything causes everything else. In the book that I mentioned at the start of this, the example that's given is the invention of rock and roll and the fall of the Berlin Wall. Two things that seem to be unrelated. But the people who brought the Berlin Wall down had rock and roll songs playing in their head at the time. So you can't say that the fall of the Berlin Wall happened independent of the invention of rock and roll. Even though one does not directly cause the other, it's still within the light cone that led to the point in space that is the fall of the Berlin Wall. So light cones are really a concept that's used to describe how information travels through time and describing a causal relationship between everything that has happened and every event that could be affected by what has happened. And there's a diagram in the book that I'll share with you guys here. You have the present event, future events that could be caused by it, and past events that could have led to it. And there's many, many causes for any individual event, and any individual event will have many repercussions down the line. This is a concept that is referred to in quantum gravity as the causal structure of the universe. So how do light cones relate to the physics? Well, essentially, massive objects attract things to it. Massive objects in space, the structure of space-time, the geometry of space-time is influenced by the way that these massive bodies attract the light cones, the light towards them, the way that they attract future events towards them. In this sense, gravitational waves, which are caused by moving gravitational objects, could be seen as being an oscillation of these light cones, an oscillation of possibility itself. So general relativity essentially describes a causal relationship between all of the things that exist in the universe and how they all interact to come together and form a past and a future. So now we skip ahead and talk a bit about uncertainty in how it relates to fields. And this is quantum field theory, which we've referenced in the past. And this is going to be how we justify the fact that there is energy throughout all of space and time. Essentially what happens is that we know that there are fields even in empty space because of uncertainty, because you can't know exactly where a particle is in space and time, because you can't measure both the electric and magnetic component of a field exactly. If you measure one, then the other one is uncertain. So when something is uncertain in quantum mechanics, that means that it exists everywhere in space and time. Even if you were to try to cool some section of empty space down to zero, so that you could have zero energy in that space, you would find that you still could not have zero energy because there would be random fluctuations in electricity or magnetism in the fields that exist in that space because of uncertainty. And we call those quantum fluctuations. We call that quantum energy or 0 point energy. If there was truly nothing in that space, then we would be able to know with certainty that a particle was not moving, or we would have to be able to know with certainty both the position and the momentum of a particle at the same time, which we just can't do. That's the uncertainty principle. So there's really no such thing as nothing. Now, the quantum fluctuations can't be detected with any traditional instrument because they technically don't have any energy, right? They technically are nothing. But if you were to put some kind of instrument at an acceleration through that space, now you're going to start to detect the energy because the accelerating object that goes through the space influences it in such a way that it gives it energy so that you can detect it. There's an experiment called the Einstein Podolsky Rosen experiment that describes creating two photons that are entangled that travel in opposite directions, obviously at the speed of light, because photons are light, remember. And what happens is that one of them is beyond the horizon, right? Because you can only measure the one that's heading towards you, because the other one is traveling away from you at the speed of light. So there's nothing that can travel fast enough in order for you to be able to measure it. And because they're entangled, if you measure one, then you're going to find that you understand the properties of the other even faster than light, because particles, again, remember, don't have to obey physics the same way that we do. They can fold through time in ways that we with our instruments cannot. And so each photon that is measured, each oscillation in this electromagnetic field that is measured by a person accelerating through a vacuum is going to have a corresponding electron that is beyond the horizon, beyond what they can see or measure. This means that part of what you would need in order to provide a complete picture of what's going on is hidden from view. It's beyond the horizon. It's beyond what you can see. So the result of what you see is intrinsically random. There's no way to predict exactly how the photons are moving or are going to move. There's no way to perfectly predict the electromagnetic fluctuations found in a vacuum. Random motion in physics is the definition of heat. So technically, the energy is hot. And that's why the temperature of space is never completely zero. The measure of heat in a system, the measure of randomness in a system, is called entropy. And that entropy, that chaos, as it's called, as what it really is, within physics, is defined as essentially the number of questions required to identify the motion of all of the particles in a space, in a gas, in a part of space, in a region of space. So this gives birth to two laws, which essentially state that the amount of entropy that exists as you accelerate through space is proportional to the horizon. It's proportional to whatever information is hidden from view by the nature of the acceleration. Now, as we discussed previously, now we're finally tying everything together, okay? What is something that exists in space, in a vacuum, that accelerates everything around it? A black hole, right? So now we're going to start to talk about black holes and entropy and all of these more complex concepts, tying everything I just told you together in a way that makes it make sense. Now, when we talk about black holes, we're talking about structures that absorb all of the energy, all of the light, all of the gases that are around them. And as that happens, something has to be spit back out because entropy can't decrease. Entropy is really, in this sense, describing information. Information has to be conserved, not lost. Black holes spit out what's called Hawking radiation as a way of maintaining the balance overall across the entire universe, as we discussed previously. Because of E equals mc squared, remember back to that, therefore, this means that as the radiation is carried away from the black hole also becomes less massive. As the black hole becomes less massive, its horizon shrinks. Distance from the singularity in which things are attracted into the black hole and can't escape must decrease because the mass is decreasing, so its reach is decreasing. Note that it takes a super long time for black holes to evaporate, for black holes to shrink enough that they stop existing. It takes an insanely long amount of time. That doesn't even make sense. So this is entirely like a theoretical kind of thing here. So if a black hole is trapping information, it's trapping things inside of it that can't escape, but now it's shrinking, then we have to ask ourselves, is there a conservation law being broken? And the answer is no, because the entropy is being emitted from the black hole as well while it shrinks. If you ask the question, does the entropy of a black hole decrease as it shrinks, you could say no, it doesn't, because the Hawking radiation that is being emitted from the black hole contains a lot of entropy. So it's putting the entropy back out into the universe because, remember, as we discussed previously, entropy can never decrease. The universe is always moving towards a state of equilibrium. It's always moving towards a state of higher chaos, of entropy. And if you want it to reduce, if you want it to move toward a state of lower entropy, you have to put energy into it to make that happen. So essentially, if something falls into the black hole, then the world, the universe, loses some amount of entropy to the black hole. But the size of the black hole increases to account for that missing entropy. Then as the black hole pushes radiation out into space, the entropy of the black hole decreases, but it pushes that entropy out into the universe, so the entropy of the universe increases. So if you remember back, we discussed the fact that things only have to be conserved over the entire universe and not over small regions of the universe. And this is in support of that or as a result of that. The interesting thing about this is that entropy is essentially, in this regard, information that the black hole is hiding from us. So what is that information that it's hiding from us? The classical theory of black holes gives us no idea as to what the information might be. So what we need is some kind of quantum gravitational depiction of black holes that can help us understand what's really happening here, because using just general relativity and the physics of black holes, as we described previously, doesn't really help us understand what happens to particles that are right on the horizon or that are entangled, and that where one of the entangled particles falls in and the other one doesn't. So to sum this all up, the search for the meaning of temperature and entropy led to the discovery of atoms. The search for the meaning of temperature and entropy of radiation led to the discovery of quanta, small individual components of space-time. In the same way, the search for the meaning of temperature and entropy of a black hole is now leading to the discovery of the atomic structure of space-time. So think about it this way. When the black hole absorbs some amount of gas, some photons or other particles that are along the horizon, the entropy of the space around the black hole decreases. The amount of information that you could know about that region goes down, because now some of the information is beyond a horizon and the information can never escape that horizon because of how infinitely dense a black hole is. Entropy is a measure of the information in a region. So if there are fewer particles in the region, now you have less information to describe what is happening in that region. This would violate the laws of thermodynamics unless the entropy of the black hole goes up. And therefore, entropy is conserved or still increasing across the entire universe, even if it goes down in a single region. Since the entropy of an accelerating thing is proportional to the size of its horizon, if the entropy of the black hole goes up, then we know that the horizon must expand. So the black hole must get bigger as things fall into it. This process has to be able to go the other way as well, because black holes can evaporate. So as the black hole shrinks, there must be some kind of photons or particles created just at the horizon that are sent away from the black hole that bring entropy back out into the universe, and this is the radiation that Hawking postulated should exist, and it turns out it does. What this all essentially tells us is that there is an absolute bound, called Birkenstein's bound, to the amount of information that can be contained behind a horizon. It also tells us that the universe is, in a sense, continuous, and in another sense, discrete. It's both at the same time. It has to be, or none of this makes any sense at all. For those of you who do check out this book, you'll notice that the next few chapters are all about trying to figure out how we can quantize space in a way that is both background independent and background dependent. They don't really go into the math here, but it is kind of math heavy. It's very hard to understand, very dense, and it doesn't really help us understand anything in terms of metaphysics. So we're going to skip ahead to talk about gravitational waves. Gravitational waves are a consequence of the fact that massive objects can influence the geometry of space-time, which we've now justified in like 5 different ways across the many lectures here. When massive objects accelerate, this results in changing field. The structure of space-time literally changes, and that can have influence on the other fields that exist in that space. For instance, causing light, an electromagnetic field, to bend around a massive object. So accelerating massive objects generate gravitational waves. These are oscillations of time itself, oscillations of the fabric of space-time that can influence and affect other fields, including physical matter. And therefore, the generation of oscillations within the energy of the universe itself, the strings, the components that make up the particles and forces and other things. We talked about the standard model and string theory in the past couple lectures, and what strings really are just vibrating bits of energy, vibrations of space-time itself, and the different particles are created by different types of vibrations. The different way that strings vibrate, the different way that these little bits of energy vibrate, is what determines which particle is which, and therefore how all of the forces behave. So all matter is really created and affected by the movements of things through space-time. And there are different particles in each universe, like we discussed in the previous lecture. There are many universes, right, that could exist. And each of those universes exists differently because of the different types of wiggles within that universe, the different types of vibrations that the strings experience. So the wiggling strings that send ripples through the spin networks define everything that physically exists and how it connects to everything else. But these wiggles, these strings themselves, cannot see the discrete nature of the spin networks or of space-time itself, so they view the universe as continuous. The way in which these vibrations weave together describes the physical universe, exactly like a tapestry of woven threads would. So the intuitive understanding of the universe as being like a tapestry of woven threads is exactly accurate. That is the math. That is the math. That is how the math works. So the analogy given in the book is that space can be woven from a network of loops called spin networks. And that's exactly the same as how cloth is woven from a network of threads. The analogy is pretty precise. The properties of the cloth are explicably in terms of the kind of weave that binds all of the individual threads together. So the way that the threads are knotted and linked together is what determines what type of cloth you have. And also the content of the individual weaves is what determines what kind of cloth you have. So if the universe is like a cloth, if space-time is like a cloth, then the vibrations of energy in these spin networks and the way that these vibrations then propagate through the spin network is what affects how space-time exists and how it functions. That the universe is both background independent and background dependent. It is both continuous and discrete at the same time. And some parts of the universe see a continuous spectrum, and some parts see a discrete spectrum, and those different parts make up the different realms, the astral realm, the quantum realm. And the physics is literally different based on what questions you ask and what answers you're looking for. So this is a lot of technical information, and we're going to get into, and this is a long video, so we're going to get into the metaphysics of what all of this information means in the next video. The important takeaways here are this. Non-action is impossible. There's no such thing as nothing within the confines of the known universe. Outside of the universe, there's nothing. Remember, what is the universe expanding into? The future. It's expanding into nothing, okay? It's expanding in a fourth dimension. It's not expanding into another physical dimension at all. All of the physical dimensions are contained on the surface of the expansion. It's a three-dimensional space expanding into a four-dimensional space, as we discussed previously. Another takeaway is that entropy is information because it describes what must be known in order to predict the precise movements of otherwise random processes. When that information is sucked into non-existence, into a black hole, when it's trapped behind the horizon of a black hole because it can't move fast enough to escape, then some new information must be transmitted back into the universe. And it doesn't always have to happen immediately. It has to be conserved over all of space and time. So it can seem like entropy is decreasing for a time, but overall it's not, because eventually entropy will increase. And the amount of information present in the universe can only increase. The amount of entropy can only increase in the end. Information is affected and generated by the movement of massive objects through space. And the movements of massive objects create energy vibrations. Information is affected and generated by the movements of massive objects through space-time. And the movements of massive objects create energy vibrations that are on the highest level, both discrete, meaning countable, meaning broken into individual bits, and continuous, a spectrum of things that can't really be counted or broken up. And the way in which all of this plays out varies in specific ways based on the cosmological parameters that we mentioned in previous videos. So these energy vibrations are what define the world. They are omnipresent. They are within us and around us. They are creating a world that is simultaneously finite, with a limited amount of information and infinite, as in expanding into space beyond and faster than you could reach the horizon. You could travel forever and never reach the edge of the universe, because you can never travel faster than the expansion of the universe. So if these takeaways don't make sense, then you should go back to lecture 4 and lecture 5 first, watch them again, and then come back here and watch this again. Know that this is incredibly hard to explain without math. So I kind of did my best. And I hope that all of this makes sense to you. If you have any questions, I'm really happy to try to answer them in the comments. Or like I said, you could join our Discord server at openmindedpath.com. And I would love to talk about this with you. Obviously, I'm very interested in physics and metaphysics. And everything in this video that we discussed today has been physics. As crazy as this all sounds, as much as it doesn't make sense, we have not discussed any metaphysics in this video. We have only talked about the physics, conceptually what is going on in the universe. And in the next video, we will use this and everything we've discussed in the past lectures to build a theory of everything, of literally everything, including science and religion, that helps us justify things like the existence of God or higher consciousness, that helps us justify all sorts of crazy things, and of the power of intuition in order to understand these things in a way that is not scientific or mathematical or objective, but still valid. So ask your questions. Let's make sure you understand the science completely, and then we'll move on to tying it all together. From everyone here at the Coven of the Open Mind, blessed be.